Faruk hocam.
Tamam. Değerli hocalarım hoş geldiniz. Ufak bir gecikme yaşadık. Kusura bakmayın. Öncelikle.
Hocam şu an YouTube'a da bağlıyız. Oturum sürelerini ben
Tamam.
Size mesaj olarak atacağım Zoom üzerinden.
Tamam.
İyi oturumlar diliyorum.
Teşekkür ediyorum. Sağ olun. Değerli arkadaşlar, değerli hocalarım hoş geldiniz öncelikle. Oturumumuza birazcık geç başlamış olduk. Dear participants, welcome to this math session. I am sorry for delay because of technical problems. The first speaker is Muhammed Celil Ahmet. And please do not forget that each participant has 15 minutes, including question session. Let's start. Do we have the first speaker, Muhammed Celil Ahmet?
Yes, I am here.
Okay, please start. Şey yapalım, ekran paylaşımı hakkı verelim. Do you have screen?
Paylaşabilir hocam.
Tamam. You can share your screen. Okay.
Okay, so do we have my screen?
Yes, we have your screen.
Okay, so in our study, we have solved a differential equation with an initial value problem condition using the optimization. And here we have preferred to use the adaptive Naldermid simplex algorithm. And I have done this study with my professor, and his name is Faruk. So without further delay, as I said earlier, in this study, we have solved a differential equation. We have used adaptive Nalderman simplex algorithm, which is also a derivative-free optimization algorithm, which means it hugely decreases our workload as we do not have to calculate the derivatives of our function. For the neural network, we will use a feed-forward neural network in this study. So before getting to the adaptive Naldermid algorithm, first we have to understand what is a standard standard Naldermid algorithm. So a standard Naldermid algorithm is a direct search method for unconstrained optimization problem. So what are the unconstrained problems? First, we have to understand that. Let's consider a function x squared minus 5. So we are trying to minimize this function. So if we do not give any conditions in this problem, then this is called an unconstrained optimization problem. And for this particular function, the minimum value will be minus 5 and the minimum point will be x equals to 0. But if we give a certain type of condition, let's say our x should be in this range, let's say 1 to 6, then this type of optimization problems are called constrained optimization problem. But for Naldermid, we will only consider the unconstrained part of this thing. First, let us take a function from Rn to R. We will call this our objective function, and this the n will be the dimension. So our simplex will be a geometric figure with n dimensions and n plus 1 vertices. If we consider R2 a function in R2, then our triangle, our simplex is actually a triangle with 2 variables and of course with 3 vertices. And on each iteration, we will calculate or evaluate the value of our function, and we will arrange the vertices accordingly. The vertex with the biggest value will be called the worst vertex, and the vertex with the best value, or the as we are doing a minimization problem here, with the least value will be called the best vertex. So without further delay, let's take a look on how the algorithm works. On the first step, we are evaluating our function, as I said earlier, on the vertices of our simplex. And according to that values, we will order our points like this. After this step, we will get to our next step, which is called the reflection point. And in this step, we will introduce another point which will be actually the reflection of the point which we classified earlier as the worst point. And this point will be called the XR. Now we will again evaluate the value of our function on this point, and if the value of this function is less than the initial value which we calculated in the first step, then this is the point which we were trying to find. Otherwise, our search will be continue, and we will get to the step number 3. So before getting to step number 3, let's us consider that we are working in R2, and our simplex is a triangle, and we have calculated our values, and we have classified our points at the worst point, our best point, and the good point. This was the first step. In the second step, we will take the reflection of this W point, which will be on this side, and we have calculated the value of our function on this R point as well. And if this is the value is less than the initial value, then this is the point we were looking for. Otherwise, as I said earlier, we will get to our step number 3. So the step number 3 is a expansion. In this step, again, we are defining a new point which will be called the XE point, and again we will evaluate our function on this point. And if the value of our function is less than the value which we calculated on the reflection point, then this is our new point. Otherwise, again we will get to the step number 4. So before getting to step number 4, let's consider the example which I gave earlier. R was our reflection point. Now expansion, after calculating our function on the R point, we couldn't find the less value of our function. Then we expanded our triangle like this, and in this step, in the third step, we calculated the value of our function on the point E. And if the value is not what we were looking for, then we will get to the point number, the step number, 4, which is the inside contraction. So in the first 2 steps, we have reflected our vertices, then we have expanded that, but we couldn't find anything. So which means we have to contract our simplex. So first of all, we will do the inside contraction, and for that, again, we define a point using this equation. This will be called the C1 point, and again we will calculate the value of our function on this point. If the value we calculate on this particular point is less than the initial value, then this is our answer. Otherwise, the search will continue, and we will go to step number 5. Step number 5 is the outside contraction, and again in this in this step we define a C2 point, using this equation, and again we will calculate the value of our function on this point. And if it is less than the value we calculated on FR, then this is our new point, otherwise we will go to the shrinking process of our simplex. And in shrinking process, again, we are defining a new point using this equation, and we will evaluate the value of our function on this particular point. So again, let me give you example in R2. First, we reflected our vertex and we get this R point. Then we expanded, but we couldn't find the point we were looking for. So first, we outside contracted and we find the C2 point. And the inside contraction will give us the point C1. So this is how a standard Naldermid algorithm works. So what is the problem? We can ask here, what is the problem with the Naldermid function? So consider our functional, which we defined here. The thing is, if we go to higher dimensions, the reduction of this functional is hugely depends on this factor. And if we consider this factor, when we increase the number n, which is the dimension, if we increase the dimensions, then this factor converges to 0 as our n is approaching to infinity. So that's why this is the main problem with the Naldermid function. Of course, it is a very efficient algorithm, but if you are working on higher dimensions, let's say 1,000 or 2,000, you have 5,000 inputs. So it will not be that efficient as compared to with, let's say, 2 variables or 5 variables. So to counter this problem, we have the adaptive Naldermid, and the major difference between the adaptive Naldermid simplex algorithm and the standard one is we had alpha, beta, gamma, and delta variables in every reflection, expansion, inside contraction, and outside contraction steps, which were not defined according or with respect to the dimension. But in adaptive Naldermid algorithm, every single coefficient is defined with respect to dimensions. As you can clearly see, the beta, gamma, and delta, everyone is defined with respect to the value of n, which will help us to make our algorithm very, very efficient. In the beginning, I said we will solve an initial value problem in this study. So first of all, we have to convert a differential equation into an optimum.
Last 3 minutes, please.
Okay. So we have to convert our initial value problem into an optimization problem. So we can we know that we define an initial value problem like this. I have to skip some steps here as we only have 3 minutes. In the neural network, we will define a trial function, and in this trial function we have a number of unknown variables. Let me come here, it will be better to understand like this. So this is the topological structure of our neural network. The inputs, we have the inputs, this neural network is called the perceptron. We have the inner layer and the activation functions. What is the work of activation function? The activation function help us to reduce the value in like 0 to 1 generally, and this whole network will give us an output which will be called the NET, the net output of our of our neural network. Of course, there will be some errors in the evaluation of our function. So how we can calculate the errors? Of course, there is an expected value and there is a calculated value, and their difference will give us the error in our evaluation, in our calculation. As an example, we have solved this particular initial value problem. We can clearly see the analytical solution of this problem is given here. The trial function for this particular problem is given here. And coming to our the results, we have solved this one with Naldermid and adaptive Naldermid as well, and we have compared our solutions. We can clearly see here the adaptive Naldermid is much more efficient than the standard one. You can clearly see it gives us very less value as compared to the adaptive Naldermid. Also, we have compared it with the standard particle swarm optimization as well. These are our results. And if we calculate the mean square root of our test sets, this is given here.
Okay, thank you very much, Muhammad Jalil. Do we have any question? Do we have any question?
I think Faruk, Özger cannot hear us. Muhammad Jalil,
Yes.
you finished?
Yes, I am finished.
Thank you for your nice presentation. Let's continue with the next presentation. Simge, Öztunç, Mutlu, Nurettin, Yılmaz. Is anyone here? No. Kaan Özdemir. No. Ümmü Gülsüm Koparan. Niyazi Emre Toprakkaya. Niyazi is here, I think.
Yes, I'm here.
Yes, Niyazi, you may start your presentation, please.
Thank you. Can you see my screen?
Yes, it's okay now. Yes.
Okay, my name is Emre Toprakkaya. I'm going to present a presentation about Roman domination in graph theory. Let's start with a brief introduction to graph theory. Simply, a graph consists of dots named as vertices and lines named as edges, which are connect dots and edges to each other. However, it doesn't give the geometric information, but a relation between vertices. Mathematically, a graph is a pair of sets G equals VE, where V is the set of vertices and E is the set of edges, formed by pairs of vertices. A graph G is finite, undirected, and simple with the vertex set V and edge set E. In a graph, if there is at least a path between every pair of vertices, then we say the graph is connected. But when it's not connected, we can talk about vulnerability. The vulnerability is the durability of the graph against the removal of some vertices or edges until the graph G is an unconnected graph. Now we are going to focus on a vulnerability measurement called domination in graphs. Especially, we are going to touch upon a historical originated type of domination named as Roman domination. An area of graph theory, which is domination, a vertex V in a graph G is said to dominate itself and each of its neighbors, we can say. The minimum cardinality among the dominating sets of G is called the domination number of G and is denoted by gamma G. To get a better understanding of the domination in a graph theory, think about a military unit. Each military unit, from the largest to the smallest, has a very clear chain of command. Therefore, there must be a free-flowing communication between the commanding echelon and soldiers. For easy command, each soldier must be placed directly under a commander's command. We give an example of a battalion's graph model here, but the time is short, so I'll skip it. In 1977, Cocaine and Hedef published a survey, and in this survey paper, they are first to use the notation gamma G for the domination number of a graph, which subsequently became the accepted notation. In this paper, we consider the Roman domination number of some special graphs known as path, cycle, comet, double comet, and com graphs. And then we compute the Roman domination number for Mischassi of the same graphs. Let's start with Roman domination's historical part. In the 4th century, the Roman Empire fought against the internal riots and the attacks of the Germanic tribes coming from north and east of Europe. Because of these struggles, the imperial army had lost most of its muscles, so Emperor Constantine had to find a way to protect the imperial lands. He developed a military rule for his remaining army units. The rule is like this: if a region had its own army or had a neighbor region with 2 units army, then region was secureable. So when a threat occurs in a non-armed region, neighbor region with 2 units army had to send one of its armies. Basically, Constantine's rules were like this, and the situation were like this. A region is secureable if a piece can be moved to it in a single step from an adjacent region, and at least 2 pieces must occupy a region before a piece can move out of it. In real life, Roman domination also models other facility location problems. For example, a communication network, or we can consider the airport's location by Roman domination. If a city has no airports, but you can go easily by public transportation within 1 or 2 hours to another city which has an airport, then there is no need to build an airport to this city anymore. Just improve the conditions of the existing airport. Now, let's make some mathematics of it. A Roman dominating function, RDF shortly, on a graph G is a function f from V to 0, 1, 2 set, satisfying the condition that every vertex U for which f of U equals 0 is adjacent to at least one vertex V for f for which f of V equals 2. For an RDF, we suppress the argument and simply write V0, V1, V2. So we can equivalently write f like this. The wave of a Roman dominating function is the value of this sum equation, which equals absolute V1 plus 2 times absolute V2. The minimum cardinality among the Roman dominating sets of G is called the Roman domination number of G and is denoted by gamma Rg, which we are going to present in this paper. In 1955, there is a other concept occurs. Mischassi published an article And with this article, the term Mischassi or Mischassi graph of an undirected graph video. It's a construction like an algorithm. The Mischassi or Mischassi graph of an undirected graph is a larger graph formed from it, but by a construction which preserves the property of being triangle-free, but increases the chromatic number. By applying the construction repeatedly to a triangle-free starting graph, Mischassi showed that there exist triangle-free graphs with arbitrarily large chromatic number. Here we see definition of Mischassi construction, and the figure shows us Mischassi construction for C5, which is a cycle with 5 vertices. You can see Mischassi construction applied to it. There are several properties for Mischassi graphs of a graph, some of them given under, like if G has chromatic number K, then mu G has chromatic number K plus 1. And if G is triangle free, then so is mu G. This is Mischassi findings, and after him, Fisher and McKenna-Boyer found that if G has domination number gamma G, then mu G has domination number gamma G plus 1. Now we give the definitions of path graphs we used, because if you don't have information about graph, we see figure P4, which is a path graph, and with 4 vertices in here. After that, we can see C5 cycle graph with 5 vertices, and 3 cycle also we gave here because we are going to use it in Mischassi graphs of the graphs, which is triangle free. The triangle we mentioned about it, it's the 3 cycle here. After that, we gave comet graphs definition and double comets definition here, which we are going to use for Roman domination numbers, and the com graphs definition here. There are some special graphs, and we are going to find Roman domination numbers of them, and we are going to apply Mischassi constructions for some of them. Here we see a proposition from Cockayne for the classes of paths Pn and cycles Cn. Gamma R Pn and gamma R Cn are equal to each other and equals to 2n divided by 3. You can see here. And Ezmi found that for each graph G, gamma R G plus 1 less than or equal to gamma R mu G, and it is less than or equal to gamma R G plus 2. We gave this proposition and the theorem first because they are related to following theorems which we are going to give. Here, our first theorem, it's about comet graphs Roman domination number. Here is the equation for it. After that, we found the Roman domination number for double comet graph, and its equation like this with modular. You can find that. And lastly, for Roman domination numbers, we found com graphs domination number with this equation here. However, it's obvious to see that Roman domination number of path graph less than Roman domination number of com graph. We highlighted that because we know that com graph is a derivative of path graph. In Theorem 5, we are going to show you path graphs, Roman domination number for Mischassi of a path graph. And we compare it with its Roman domination number here. In Theorem 6, also we showed cycle graphs, Roman domination number of Mischassi constructed one, and we compare it with Roman domination number of cycle graph also. Corollary from Theorem 5 and Theorem 6, we could say that they are equal and they're equal to this equation here. This is our references, and thank you for your attention and patience.
Değerli hocam, çok teşekkür ediyorum. Sağ olun güzel konuşmanız için.
Thank you. Teşekkür ederim hocam.
Hocam biz teşekkür ediyoruz. Sağ olun. Sorusu olan hocalarımız var mıdır? Sorusu olan hocalarımız. Tamam. Hocam eklemek istediğiniz bir şey yoksa teşekkür ediyoruz tekrardan.
Çok teşekkür ederim hocam. İyi çalışmalar.
Verdiğiniz
Niyazi,
güzel sunumdan dolayı.
Emre teşekkür ederiz.
Çok teşekkür ederim hocam. Sağ olun.
Güzel bir çalışma oldu. Graf teori benim çok alanıma girmese de çok popüler bir şey haline geldi, konu haline geldi. Özellikle işte yapay zeka ile ilgili bağlantısı gerçekten dikkat çekici.
Sağ olun hocam.
2002, 2003, 2004 hocam bu hocalarım yok görünüyor şu anda. Tekrar kontrol
hocam.
edeceğim.
Ali Mutlu hocamı aradım az önce.
Evet.
Rahatsız olduklarını, katılamayacaklarını, sağlık problemleri varmış
Evet.
herhalde hepsinin.
Hiçbir
Katılamayacaklarını bildirdiler.
Anladım. Evet. Dolayısıyla ilk oturumda eğer Ali Hoca'nın ekibi katılamayacaksa ilk oturumda konuşmacımız kalmamış oluyor Mehmet Hocam.
Yanlış oldu, evet.
Bir ara vereceğiz. Diğer oturumu zamanında başlatalım diyelim.
Evet.
Diğer hocalarımız ona göre hazırlıklarını yaparlar. Mehmet Hoca'nın ekibi, Mehmet Sezer Hocamızın ekibi. Saat 11:15'te tekrar toplanmak üzere diyelim. O zaman oturumu kapatalım.
Teşekkür ederim.
Uygun mudur Mehmet Hocam?
Uygundur hocam. Teşekkür ederim.
Tamam. Çok teşekkür ediyoruz değerli katılımcı hocalarımıza. Saat 11:15'te programda verilen bilgilerle tekrardan sisteme giriş yapmış olacağız. Emre Hocam tekrardan çok teşekkür ediyorum güzel konuşmanız için. Görüşmek üzere diyorum.